Okay, in this problem I have a 10 kilogram block that's sitting on some type of surface. I have a 30 Newton force being applied at a 50-degree angle coming off the horizontal, a 20 Newton force here being applied coming off the horizontal with a 40-degree angle. I want to find out what the frictional force would have to be along this surface here so this object has constant velocity. Now the thing we know, we'll call this our x-axis, is we know the summation of forces along the x direction must equal to mass times acceleration. Oops, hang on a second. Got a delay here, sorry. That's equal to mass times acceleration, and here acceleration equal to 0. So we can say the summation of forces in the x direction must equal to 0. And that's because we have constant velocity. Alright, so let's draw our force diagram or free body diagram first. We'll have 10 kilograms here. That's 10 times 9.8 meters per second squared gives me 98 newtons coming down. Draw that with a vector real quick. I have this 30 Newton force coming through like this. I have a 20 Newton force being applied here. And I have a normal force coming back up. And the only thing I know is I got some frictional force that's going some direction. Right now I don't know whether it's going this way or going this way. So we'll just go ahead and indicate what direction we think it's going to go. Now we will label everything. We had 30 newtons here. This will become our 30 newtons passing through here. Our 20 newtons will be over here. This will be, we call it the force. It's going to be kinetic friction. I like to do this, comma, what's it acting on? It's acting on the block. And what's causing it would be this type of surface, so we'll just give that an S. This is our force of, it's caused by gravity, comma, what's acting upon it is being acted upon by the block, and what is causing that is Earth. And we'll set that equal to 98 newtons here. Here we have this will be our normal force. Again, what is it acting upon? Acting upon the block, and what's causing that would be the surface. So that's our force diagram, or free body diagram. And now what I like to do is I like to break each one of these into its components, and you can do that separately if you'd like. We'll do the 30 Newton first. I come over here. Again, I draw the components. Remember, you always start with tail here. You'll come back head here. I'll go ahead and extend this on out. Close, it should line up perfectly, but now we know this angle here is 50 degrees. We know this is 30 newtons. So we can say this component here would be 30 times the sine of 50. And that's going down. Here we'll have 30 times the cosine of 50. That's going to the left. We'll do the same thing for the 20. Let's come up here and do it right here. We draw a vector here. Again, we start tail, we come down, come over like that. This angle here we know is 40 degrees here. We know this magnitude is 20. So this component here would equal to 20 times the cosine of 40. That's going this way. This one here would be 20 times the sine of 40. It's going down. Alright, so at this point, honestly, you can draw yourself another free body diagram with the components being added. And I like to do this. It goes into a lot more detail. But if you do this, it's really difficult to make a mistake. Again, just drawing arrows here. Now we can label everything. So when we come back and look, what do we have coming to the left or coming to the right? The only thing we have here is 30 times the cosine of 50. That's that one here. I have no other force going to the right. What do I have going to the left? Well, I have 20 cosine 40. And I have the force of kinetic friction going this way. What do I have coming down? Well, we can come back to this one. We have 30 sine of 50. I have 20 sine of 40 coming over here. Scroll up a little bit. And I got my force of gravity, 98 newtons coming down. So that's all the forces, and nothing says, too, that you can't just put these on the end like this, too. You can do that, too, if you prefer. It's your choice. So at this point, all we have to do is sum up the forces in the x. Now, I'm not going to sum up the forces in the y. We can to find out what I should have labeled this, sorry, F normal. If you want to find out what the normal force is, but here we're only looking for the frictional force. So we're going to set this up to 0. So we start out here. I got minus 20 cosine 40. Come to the left. I have, we can go ahead and do this one, minus the force of kinetic friction plus this one, 30 cosine 50. And we set that equal to 0. We're going to go ahead and add this one and this one. Oops, hang on just a second. Jumped on me. We're going to add these two here together first. I'll get the calculator. Minus 20 times the cosine of 40 plus 30 times the cosine of 50. So what I have here is I have minus Fk plus 3.963 is equal to 0. I move this to the other side, and that'll give me F of k is equal to 3.963. Again, when I move this to the other side, I get the negative, then multiply by the negatives, then I'll get this value here. So now, since you got this positive, you know that kinetic friction must be going back this way, and that would equal to newtons. And that's the problem. That's all you have to do on this problem. Okay, I hope this detailed solution helped you. Again, I like to draw the force diagram or free body diagram the way it is, and then I like to draw another one with the components, and then pretty much add everything that's going in the x direction, add those together, set to 0, add everything on the y direction if necessary, and set those equal to 0. Okay? Alright, best of luck.